We're going to spend probably 2 full weeks, maybe a bit more, looking at what we call kinematics. That's what it has in the little title up there. Unit 3, kinematics equations. Kinematics is the study of how things move. It's the physics of how things move. You're going to learn the 4 kinematics equations. You're going to find actually in Physics 12 you don't learn any more kinematics equations. You just learn how to apply them in ever complicated situations. But it's going to seem a little intimidating at first. I've done this before. As long as you don't quit on me, you will have your aha, I just all got it together moment. It's going to click at different rates for different people. You're going to, at one point or another, seem a little bit a little confused. I don't quite know what's going on. I get that. Some people will pick this up. Some people will take a bit longer. And part of it is I'm really going to push you, Nick, to do a lot of this in your head. I hate memorizing crap. And so I'm going to bite the bullet from day one and try and teach you to derive things using something we call formula manipulation in your head. I'm going to make you do a lot of algebra in your head. And if you're not great at that, you will get good at it. Trust me. I've done this before. But at first, it's going to seem like I'm speaking and none of the words make any sense. I also know that as well. As long as you don't quit on me, we can do this. But if you quit on me, I'm a pretty good teacher, but if you just decide to take the F, there's nothing I can do. So don't quit on me. If after a week into this, you're still totally lost, then we'll go from relaxing to mild worry. And what I mean by that is you probably want to check in with me for an after-school session, maybe a flex session. I would normally say a flex session, but right now I'm only seeing you for flex once a week, which is not enough. So after schools, I'm free, and that works great for me one-on-one. Are you ready? Here we go. In physics, every measured quantity is one of 2 things. It's either a scalar or a vector. Anytime I introduce something new to you, but I'm going to tell you, first of all, the abbrev, the symbol, usually a letter, the units, what we measure it in, and whether it's a scalar or a vector. And you'll have to memorize those 3, but I would say to you, you won't need to go out of your way and make flashcards, or you'll memorize it through sheer repetition and laziness, which really, again, is the best way to memorize something. Okay? What's the difference between a scalar and a vector? Well, scalars have magnitude only. Size, that's the fancy word for size, is magnitude. Let me give you an example. 25 meters per second. Vectors have both magnitude and direction. Let me give you an example. 25 meters per second at 32 degrees west of south. That's an at symbol, like Shift 2 on your keyboard, like in Twitter names. 32 degrees west of south. This here is Physics 12. In Physics 12, we redo Physics 11 again, but in 2 dimensions. This year, we're going to be doing 1-dimensional physics, so our way of showing direction is going to be positives and negatives. If we're going forwards, we'll call that positive. If we're going backwards, we'll call that negative. If we're going up, we'll call that positive. If we're going down, we'll call that negative. So we're not going to get into the so many degrees of what. Both of these, I'll take your question in a second, both of these have the same magnitude. This one also has a directional component. Question? West of south? Nope. West of what? West of what? Say it again.
South.
So west of what? I'm not making fun of you. That's how I teach it in grade 12. To draw that, you would go south first. What of south? How far? 32 degrees, about like that. Where that's a 32 degree angle. This is how, I just snuck in a quick physics 12 lesson. We spent a whole day on this in physics 12, figuring out how you do compass directions, but it would be like that. Southwest would imply exactly 45 degrees. South-southwest would imply 22.5 degrees, half of 45. So, scalars and vectors. Okay? Speed is a scalar. That's what appears on your speedometer in a car. Doesn't have a directional component. It's just how fast you're going. Velocity is a vector. That's speed plus direction. Mr. Dewick, yeah, Reed. Is there a dumb, easy way that I could remember that velocity is a vector and speed is a scalar? Mr. Dewick, if you were a good teacher, you'd have an easy way for me to remember that velocity is a vector and speed is a scalar. Reed, you're right. I'm sorry. I got nothing. You'll have to figure it out on your own because I can't think of any way to remember that. Time is a scalar. How long was the movie? 2 hours north makes no sense. Even how long was the movie? -2 hours makes no sense. Well, I watched a movie where they went backward and cut. No, there's time is a scalar. It's going to be positive. Okay. Acceleration is a vector. If your acceleration is positive, you're speeding up. If your acceleration is negative, knock knock, you're slowing down. Makes a difference. The tricky one that I don't have a dumb, stupid thing like velocity is vector and scalar for speed is distance is a scalar. Displacement is a vector. And the reason I don't have a good one is they both start with D. In fact, they both start with DI. In fact, they both start with DIS. If you come up with a clever way to remember that distance is a scalar and displacement is a vector, let me know and maybe I'll use it for the rest of teaching and give you credit for it. But I haven't come up with something dumb and obvious for that one. That one might just be brute force memorization. And then there are a whole bunch more that we'll get into, but these are the ones we're going to be looking at primarily in this unit. Vectors are written in a textbook in bold font. Look up, but don't write this down. If I want to show velocity, a textbook would bold font it, but for handwriting, that's kind of dumb. So what we do instead when we're handwriting symbols is we put an arrow above them. Don't write this down, just look up. That's a velocity vector. Although we get a bit sloppy, we don't even do the full arrow, we just put a little half arrow tip on the top. The symbol for velocity is, first of all, the abbrev is a V, which makes good sense. And then the vector to remind us it's velocity. The abbrev for speed is that. It's the velocity symbol, but no vector. That's our way of saying, psst, just magnitude. Why isn't speed S? Because that's taken by something else, and we don't have enough letters in the English alphabet. Okay? So you can write this down if you want to. That would be the velocity vector for acceleration. We'll use a lowercase a for acceleration. That would be force. Force is a vector. Force is a push or a pull. It matters which way you push on something. Pushing it from behind will make it go forwards. Pushing it from in front will make it go backwards. Makes a difference. So everything is a scalar or a vector. We show vectors with vector symbol, vector arrow. Let's talk about distance and displacement. This is both easy and confusing. How can it be both? Trust me. Lena, that was a long blink. You gonna make it? Yeah? Okay. Distance is how far an object has traveled. Ah! Okay. There you go. Sorry, YouTube. I get great comments in some of these when I do that because people have headphones on and they got it cranked. Well, they're awake now, so sorry if you're watching this on YouTube. Symbol. Don't write this down. The correct British symbol for distance comes from Sir Isaac Newton, who is the father of modern physics, of classical physics. He used a word from Latin, and so don't write this down. He liked using a lowercase s. I hate using a lowercase s because my s's look like fives, and almost no one does that. But if you do your engineering in Britain, because Isaac Newton was British, they'll all use an s. Don't write this next bit down. Many textbooks will use an x because you're on the x-axis. They'll just want you to imagine you're on a graph sliding back and forth. And so let's use the letter X like we're sliding along the number line. And that's okay. I'm going to use as my abbrev a letter D for distance. Write that down. That's terrible teaching, Nicole. Right now, a physics prof would be screaming at me because the letter D, a lowercase d, actually means something hugely important in calculus. But are we doing calculus right now? Well, then I'm going to use a D for distance. Units. Distance is measured in meters. The SI unit for length. Displacement is an object's change in position. Symbol, don't write this down. It should be, because that's what the Brits would use, or it should be, don't write this down, that if you're moving left or right, that if you're moving up or down. Write this down. I'm going to use D for displacement with a vector symbol over it because that's easier to remember. What's the difference between distance and displacement? The easiest way I know to explain the difference is for me to go for a little walk. Sorry, those of you who are watching on YouTube, you can't see this, but the rest of us. I'd like you to imagine that each step that I'm taking is 1 meter long. Count with me. 1, 2, 3, 4. What's my distance? 4. What's my change in position? Also 4. Ready? Count with me. 1, 2, 3 forward, 1 back. How many steps did I take? 4. So what's my distance? 4. What's my displacement? 2. 3 forward, 1 back. 2. Count with me. What's my distance? 4. What's my displacement technically? 0. Count with me. What's my distance? 3. What's my displacement? -3. So you get the directional component there. Displacement is your change in position. Basically, you look at where you ended up, you look at where you started. That's your change in position. Distance asks, how'd you get there every step in between? Displacement doesn't care. Is that all right? So when objects start moving, it's useful to be able to describe an object's location. To describe location, imagine a meter stick is placed next to the object, and the meter stick acts kind of like a little number line. Objects to the right of 0, we'll call them positive. Objects to the left of 0, we'll say they're in a negative location. You could also use right and left or east and west, but those are all too much writing. I would take them, but let's use negative and positive. So I'd like you to imagine we have a little bug that's walking on this number line. And what it does, it starts at A, it walks to B, then it turns around and walks from B to C. There's its path. Draw that in. What distance did the bug walk? Well, distance, d with no vector, 4 plus, from A to B was 4 meters, and then from B to C was how many? Careful, do the math carefully. I think 10, yes? From positive 4 to negative 6? What distance did the bug walk in meters? Do the math in your head, please. 14 meters. What's the bug's displacement or change in position? Where did it start? 0. Where did it end up? Its change in position is negative 6 meters. Or 6 meters left. Which of those two is less writing? I'm going to use the negative. You can use left and right if you want. Here's where I would take marks off. If you told me negative 6 meters left, what's negative left technically? I would argue you've just told me it's gone right. So use one or the other, but not both. Turn the page. Example 2. Suppose you run along 3 different paths from location A to location B. Along which path, or paths, would your distance traveled be different than your displacement? Or let's flip this on its end. See those 3 paths? In one of them, your distance and your displacement would have the same magnitude. Which one? Middle one. In the other 2, your distance and your displacement will have different magnitudes. So, because that would be your displacement, A to B. Your distance would be that zigzag. And because that would be your displacement, and your distance would be the squiggle. So far, so good, Dan? Okay. We can use arrows to represent a displacement. So here's an example of a bike moving along a number line from a position of 4 meters to negative 3 meters. We'll often use a variable, sometimes x because it's a number line, but I prefer d for distance displacement. And subscripts will often use a lowercase I for initial and a lowercase f for final. So if you wanted me to label this bike, I would call this D initial and D final. And because I have people sitting in the back corners, whenever I do a lowercase I, I'll put a little curly tail and the dot, so hopefully you can tell that's an I and not a 1. Sometimes the dot doesn't photocopy properly, but you'll still see a little, I'll do almost an italics kind of an I, just to have it. Okay. So example 4, draw an arrow showing an object that moves from the negative 4 position to the positive 5 position. Here's D initial. There's D final. What's this object's distance? Yeah, 9 meters. d equals 9 meters. What's this object's displacement? I need a direction. What would be a shorter way to write right? If you didn't put a plus sign, in math we say, look, we assume a number is positive unless you say different. So honestly, you wouldn't need to put the positive here. I would clue in because you put a vector symbol above the letter D that you were giving me a displacement. You can see, Danica, we pack a lot into the notation here. I wasn't kidding when I said we tend to abbreviate. Example 5, draw an arrow showing an object that moves from 7 to 1. So here's my initial location. Here's my final location. What's this object's distance? What's this object's displacement? Yep. Mr. Duick, if it was more complicated, is there a way I can get that? Yeah. Displacement, or your change in position, is always going to be final minus initial. In fact, if you look on your green sheet, in the top right corner on your green sheet on the front page, or at least it used to be in the top right corner, maybe it's one line down, somewhere I have delta triangle equals change. Oh, the first thing. Do I say change in equals final minus initial? Is that what it says on the very first? Yeah. You can take that to the bank anywhere. Anytime there's a change in, it's final minus initial. So that's distance versus displacement. Let's talk about speed versus velocity. Which one is the vector? Velocity, speed's the scalar. Okay. We're going to talk about average speed and average velocity because I haven't taught you how to accelerate yet. So we're just going to take an average. We'll get to acceleration and instantaneous speed and velocity in a couple of days. But for now, average speed is distance over delta t. What do you think t stands for? Time. Where that delta means changing. As an equation, speed equals d over, and then pause and look up and don't write this next bit down. Change in anything is final minus initial. Technically, Liza, I should go t final, don't write this down, minus t initial. But time is unique. It shows up everywhere in physics. And by definition, it's always a change in. There's no way to measure time without starting a stopwatch and stopping a stopwatch. And your stopwatch goes final time minus initial time for you. So we get sloppy. Even though time is always a delta, we just forget writing the triangle or the final minus initial in front of it. We just kind of do that. Let's write that down. Speed is distance over time. I think I gave that to you on your formula sheet. I think second line. That's also my way of saying, look at your green formula sheet so you know where it is so you can find it if you need to. What would the units be? What do I measure distance in? What do I measure time in? So what do I measure speed in? Meters per second. Scalar or vector? Speed is a scalar. What that means is if you see a number and next to it is meters per second, probably a speed. Average velocity, so if average speed is distance over time, velocity is displacement over change in time, where the delta means change in. As an equation, velocity is displacement. And remember the speech I just did about time should be t final minus t initial, but it's always a change in, and so we get sloppy. Same thing. Brandon, what would the units be? What do I measure distance in? What do I measure distance in? What do I measure time in? You know what? This is also meters per second. So I lied. If you see a number and next to it is meters per second, you know it's a speed or a velocity. It's a vector. How can I tell which one is which? If there's a directional component, it's probably a velocity. So, suppose the bug's trip mentioned in example 1 took 60 seconds. So 60, I said 60, 30 seconds. So t equals 30. What's the bug's average speed? Well, that's going to be distance over time. Cool. Jan, how much time? Can you turn back to the bug example? I think it was example 1. What distance did it travel? My brain remembers 14, but I might be wrong. Double check me. Was it 14? Go to your calculators. What's its average speed? You get 4.6 repeating, right? My calculator rounds off there, but I'm pretty sure it just goes 6 forever, right? 14, how many sig figs? 2. 30, technically, how many sig figs? Technically, how many sig figs should I go to? I should report this as 0.5. We're not going to. I said to you, we're going to ignore sig figs for the rest of the year. Let's just give our final answers to 3 sig figs. So I'm going to go 0.467. Is that okay? Units, meters per second. Yep. If you wrote 4.6 repeating, that would be wrong. If you wrote 0.46 repeating, I probably wouldn't take marks off, but generally we are going to start to round. Actually, first of all, typically what I'll start getting you to do is often use your answer button as we do several steps of calculations, and then round off our final answer. B, what's the bug's average velocity? Didn't we just find it? No, we found average speed. What's average velocity? Average velocity is displacement over time. Callie, how much time? 30 seconds. What was the displacement from that bug example? You need to go look. My brain is vaguely remembering -6, but I might be wrong. Was it -6? So, what do you get? I get -0.2. You know what? I'll make it look impressive. I'll go to 3 sig figs. I'll add the zeros in just to make it look, meters per second. What's the negative tell me? On average, the bug was traveling backwards or left.
Wait, this is the same bug?
Yeah.
How do we know that? Oh, an example. That makes a lot of sense. Yeah.
Example 1, the bug, right there. Okay. I'm going to hit pause. We're going to start to take this concept and start doing some equation rearranging and stuff. But for now, with the remaining 10 minutes, you can work on the study guide if you haven't finished that already. You can work on I think I gave you an identical test, a practice test, if you haven't finished that already. Or you can just dream about swimming with dolphins or something. I don't know.